me put this up on board. All right, oops, that's not what I want. Okay, ladies and gents. All right, I won't take the whole class time because we don't have anything to go over as far as an assignment goes today. So I'm just going to do a few notes, a few example problems, and then you'll have some time today to work. Usually the first day of the week, I try to make it a little shorter, but today's Tuesday. So since we have a full day of class, you'll probably have about 20 minutes at the end to do your assignment. So you might be able to get done in class time. Anyway, what we're looking at today, 10.5, tangents. So there are lots of different ways that we can talk about tangents. For this diagram over here, they drew in two tangent lines. Now they give us a definition that says a tangent to a circle intersects a circle in exactly one point called a point of tangency. So in this diagram, we have a point of tangency at R. Now, whenever we have a point of tangency from a tangent line and a radius, Noah, stop talking. That's how you count. All right. So we have a right angle whenever we have a radius meet at a line of tangency. So here we have angle R is a right angle. We could also draw in other parts here. So if we drew in the radius from P to T, that would also form a right angle. And then there's lots of different properties that you can use. Right now, we have a quadrilateral over here. So we could use properties of a quadrilateral, all angles add up to 360. Or if I drew in a line from P to S, I could also have two right triangles and use properties of a right triangle. So once you know that you have your radius and tangent line forming a right angle, there's lots of different properties that you can use. Then you have these two segments, RS and TS, are also congruent. Again, anytime you have two tangent lines coming from the same exterior point, they are going to be congruent. There's also another idea that they talk about in here, but they don't have drawn. So I'm going to draw it off to the side. If I had two circles, so there's a circle, there's a circle. If I had a line, that was tangent to both circles, like that, that is a common tangent. All right. Again, we won't do a lot with common tangents, but they did define it on there, so I wanted to make sure we had a diagram of it. But again, a tangent could be a line, it could be a segment, it could be a ray, but those are the two most important properties. When a tangent line intersects a radius, it forms a right angle, or when two tangents come from the same exterior point, they are going to be congruent. Down here on the first example, they have a circle, and you notice they have a triangle drawn in. On that triangle, they have a couple pieces labeled. Now they want us to find X. There's some other very important information that's missing though in order to solve this. First off, what do we know about angle B? So look at the diagram. What do we know about angle B? It's a right angle. So since we have a radius meeting a tangent, angle B must be a right angle. Also, in order to actually solve this, you'll see in the example they're doing Pythagorean theorem. Well, in order to use Pythagorean theorem, you have to know two sides of the right triangle. We know one side is 8. We also know that this piece is 9. But we would need to know this entire side. Well, if BC is 8, what's DC going to be? It's also going to be 8. Because BC and DC are both what? Yeah, they're both radii. So since you have two radii in the same circle, they have to be congruent. So if that one's 8, this one's 8. Now that we have this is 9 and 8 on this side, we can add those together and get a total of 17 for that entire side. So you have 8, you have 17. You can now plug into Pythagorean theorem. Now, did you actually have to use Pythagorean theorem? Did you have to use Pythagorean theorem? No, because this is one of our triples. This was an 8, 15, 17. Now, again, it's not one of the main two that I asked you to memorize, but if you know other triples, they will help you do some of the work faster. Yes. I hear you. All right, we're going to go down and do a few examples now. So down here on the bottom. It says find x, assume that segments that appear to be tangent are tangent. So on each one of these, any line that looks like it's a tangent line, it's saying it is a tangent line. Now, they're using a combination of the two different properties. So first, on number one, you have BC and CD are both drawn from that same exterior point C. What do we know about those two segments? They're equal. So since we have BC and DC coming from point C, those two segments have to be congruent. So we're going to set them equal. So x plus 3 equals 7. What is x going to be? 4, exactly. All right, on number 2. Now, this one, we have a triangle drawn in. And there's other information we should already know about this triangle. What do we know about that triangle? It is a right triangle. Again, anytime we have a tangent and a radius, we can say that it's a right triangle. So if we know two sides of a right triangle, then what can we use to solve for the third side? We can use Pythagorean theorem. On here, x would be our hypotenuse. The other two would go in for A and B. Now, do we actually have to use Pythagorean theorem? No. A lot of times from this point on through the rest of the year, if we can use Pythagorean theorem, I'll at least set it up so you know what the equation is that you could use to solve. But if we can use one of our triples to do it, I'm not going to go through all the steps of Pythagorean theorem. So on here, 15 and 20, well, this is one of our triples that's been multiplied by 5. This is our 3, 4, 5 Pythagorean triple, which if you multiply those by 5 is 15, 20, and the missing part here, 25 for x. Now, on number 3, we have two tangents drawn in from point P. So what do we know about NP and QP? What do we know about NP and QP? They are what? Equal, yeah. Equal, congruent. So if we know that the one length is 12, the other length also has to be 12. So on here, that's it. We don't really have any work to do on that one. On number 4, 4 is a lot like number 2. We have, again, a right triangle. Now, they put x only on this piece, going from U to T. But before we can find that piece, we're going to have to look at this as a whole. So I'm going to call it C right now, because that entire side would be the hypotenuse of a right triangle. So again, we can use Pythagorean theorem to find that missing side. C squared equals 15 squared plus 36 squared. But do we have to actually do that? Again, this is another one of our triples. What's the other triple that you should memorize? 5, 12, 13. So this is our 5, 12, 13 multiplied by 3, making this a 15, 36, 39. So the missing side here is 39. Now, how do you just get x? Because x on this one is not this entire side. It's just that piece. We have SR, right? SR is a radius. What else in here represents a radius? RU. So RU is also 15. So if this whole side is 39 and this piece is 15, we can now do 39 minus 15, which leaves us with 24, and that'll be our x value. Down on the bottom, Same idea as on 2 and 4. We have a right triangle. Now, these two are harder to recognize as triples, and one of them is a triple, one of them isn't. But most likely, you probably don't recognize the triples on these. So we have a right angle. This piece is 21, so this piece is also 21, which makes the entire length of YB what? Why not? Just wondering, does anybody actually know this triple? I'll tell you, we're missing the shorter side of it. If you don't, it's okay. I don't remember this one all the time either. So the missing side here is 20. Since it is one that's more challenging to remember, I'm actually going to go ahead and draw the whole thing out. So I got 29 squared is equal to 21 squared plus x squared. So using Pythagorean theorem, using the calculator, plugging it in, 29 squared is 841. 21 squared is 441. Subtract off 441, you get 400. Square root both sides, and you get 20. And again, that's our missing value. All right, on number 6, last one on this page. So we have 24, 17. This one's not a triple, but it's already set up nice for Pythagorean theorem. We have a right triangle. We just need to solve for x. So x squared equals 17 squared plus 24 squared. 24 squared is 576. 17 squared is 289. If you add those together, now we also have to take the square root of that. This one, it did not tell us to leave our answer as an exact value. It didn't tell us to round, so either answer would be acceptable. 29.4 would be a good answer as a decimal. Don't actually think this makes a very nice simplified answer either. Let me look. Square root of, yeah, no, that doesn't really simplify down either. So if we left it as square root of 865, that's also fine. Questions on that first page? All right, the other side is actually a little bit easier. So the second half, if you go over to page 30 now, that piece is slightly easier. So last week we talked about inscribed polygons in a circle. Now this one's talking about circumscribed polygons in a circle. So again, a circumscribed polygon is going to be when all the sides of the polygon are tangents. So going back to inscribed, all the lines were chords. Now all the sides are tangents. So each one of the sides is touching the circle exactly once. On the top two examples, they have the circles inscribed into regular polygons, a regular hexagon, a regular square. But then in the example, they have it inscribed into a triangle, and it's not a regular triangle. It's not equilateral. So we're using some of the same properties as what we had on the last page. On here, if you know that BE is 6, what's DB? It's also 6, because both of these come from the same exterior point, and they're going to a point of tangency on the circle, therefore they're congruent. Then you have FC is 8. Well, if we know FC, we also know EC would also be 8, because they're coming from the same exterior point. Over on the last corner, we have angle A, and their segment AF is 12. If we know that's 12, then segment AD is also 12. So from each exterior point, we have congruent segments. Now, on this one, they asked for the perimeter. So in order to get perimeter, you have to add up all the sides. Now, you could add up every single one of those exactly like they did there. You had 12, 12, 6, 6, 8, and 8, total of 52. There is another way to do these for a perimeter. Since you're always going to have two of the same value, if you just take one from each of the vertices, you can add them up and then multiply by 2. So for example, 8 plus 12 is 20, plus 6 is 26, times 2 is 52. All right. Let's go down. All right. On the examples down here. So it's the same thing each time. You're just identifying what the missing pieces are, and then they want you to solve for both x. So they want you to find x and find the perimeter on each one. On the first one, they gave us a piece of each one of those corners. So I could actually do the perimeter first. On here, 13 and 17 gives us a total of 30, plus 10 is 40. Multiply that by 2, and we get 80. So again, if they give me one piece of each of those corners, you just add them up and multiply it by 2. That's perimeter. Now for x, you have to look at the other missing piece here. We have 10. So this piece was also 10. Add those two together, and we get a total of 23. Now, if you wanted to, you could go around and find all the missing pieces. So that was 10. This was 17. So this is 17. This is 13. So this is 13. And again, if you added all those up, you get the same perimeter of 80. All right. On number 2, we have this whole thing is 26. Well, I know that this piece is 18. So subtract 18 from 26. That leaves us with what? So this little piece here is 8. Now, we already know what x is. X is going to be 8. And then for the perimeter, again, if you want to add it up every single piece, that's fine. Now, since you were given this entire length, just be careful not to add that side twice because we have them labeled separately and we have the whole side labeled. So use one or the other, not both. But again, you could do the same thing. You could take 8, 18, and 14, add them up. Again, on this one, you do get a total of 80 whenever you add up all the pieces. So it is a perimeter of 80 again. On number 3, some of these do have a little bit more algebra, but not much. This one, we have 8. This is 2x. So this 2x has to be equal to 8. If 2x is equal to 8, solve, and x is 4. For the perimeter, we actually are dealing with a square here since we have all these pieces are the same. So we have 16 on all 4 sides, which would give us a total of a perimeter of 64. All right, any questions on these problems? All right, I'm going to stop there then. As far as an assignment goes, what I want you to do, your assignment is going to be page 31, 1 through 8. So I'm not making you do both pages. You can probably finish this in class time and you don't have an assignment for tonight. So page 31, 1 through 8, that's all you have to get done. Any questions? All right.